Trigonometric modeling. Objectives: model with sinusoidal functions, model periodic behavior, and model harmonic motion functions. Any motion that repeats itself in a fixed time period is considered periodic motion and can be modeled by a sinusoidal function, either the cosine or the sine function. Modeling periodic motion. Coastal areas experience tides, which are where the ocean periodically gets to a high point and a low point. Tides can be modeled with a sinusoidal sine or cosine function. At one beach, the high tide is 7 feet above mean sea level, and the low tide is 7 feet below sea level. The length of time between high and low tide is 7.5 hours. If high tide is at time t equals 0 hours, give the function h of t that describes the height of the tide relative to sea level t hours after high tide. So let's first start on the period. I know that the period P is equal to 15. Now we can get some information just from this. Period is 2 pi over b. So when I solve for b, I have 15b equals 2 pi, and b is equal to 2 pi over 15. Now, we have the beach, and we have the high tide at 7 feet above and the low at 7 feet below. So I know my amplitude is 7. Amplitude is the absolute value of A. Now, we want some function that starts at high tide being at time t equals 0 hours. Between the sine and the cosine functions, the cosine function is the function that starts at its maximum. So that will be the function we'll use. H of t is equal to the amplitude of 7, and this will be a positive 7 here because it's starting at high tide, which is normally the high is where the cosine with no reflection will start. And then I have cosine of 2 pi over 15 t. H of t equals 7 cosine 2 pi over 15 t. Outside temperature over a day can also be modeled as a sinusoidal function. Suppose you know the temperature varies between 58 degrees and 82 degrees during the day, and an average daily temperature first occurs at 8 a.m. How many hours after midnight to 2 decimal places does the temperature first reach 64 degrees? Well, the first thing I want to do is find the midline. When I look for finding the midline, I look at the highest and the lowest, and that's going to be 82 and 58. I'll add those and divide by 2 because that will give me the average. That ends up being 70. And remember, 70 as your midline is going to be D. My amplitude, in other words, how far above and how far below the midline does the temperature vary? From 70, it goes up 12 degrees to get to 82 degrees, and down 12 degrees to get to 58 degrees. So this is amplitude. we'll take 82, subtract 58, divide by 2, and that is 12. My period. The period is a daily occurrence, so we have 24 hours in a day, and we can gain some information from this. Remember, the period for a sinusoidal curve is 2 pi over b. When I solve for b, I'll multiply both sides by b and divide by 24. So b is going to be pi over 12. And I know that c is my phase shift. The phase shift, c, is going to be 8. This way I can start my average daily temperature first starting at 8 a.m. right here, and this is going to be for us a sine curve. So now we're ready to put all of the pieces together for our function. We have T of t, that's the temperature at time t, is equal to 12 times the sine of pi over 12 times t minus 8. And to bring this up to the midline, we add 70. And remember, the amplitude is the absolute value of A, but we're going to go with positive 12 anyway, because our temperature is going to start at the midline and it goes up from there, because as the sun starts coming out, the temperature rises. So there's our A value, this is our B, our C, and D. Now we're ready to go ahead and put this function to use. I need to find out how many hours after midnight, to 2 decimal places if necessary, does the temperature first reach 64 degrees. So I have here 64 is the temperature at some time t, equals 12 sine of pi over 12 times t minus 8 plus 70. And now I'm going to solve for t. I can subtract 70 from both sides. That gives me a negative 6 equals 12 sine of pi over 12 times t minus 8. And I divide both sides by 12, I get a negative 1/2 equals sine pi over 12 times t minus 8. Now I'm ready to use my inverse sine function to be able to solve for t. The inverse sine of negative 1/2 is equal to pi over 12 times t minus 8. Now if I multiply both sides by pi over 12 and go ahead and find the inverse sine of negative 1/2, this simplifies it quite a bit. The inverse sine of negative 1/2 is going to be a negative pi over 6. Multiplying both sides by pi over 12 is going to help me to clear out this right side and get it a little more simple. Multiplying both sides by 12 over pi is going to give me a negative 2 on this side equals t minus 8. When I add 8 to both sides, t is equal to 6. So we have actually an answer that is exact and doesn't need rounded to 2 decimal places, but we would have 6 hours after midnight where that temperature of 64 degrees is first reached. It'll be reached again when the day progresses and the temperature starts lowering. A Ferris wheel is 45 meters in diameter and boarded from a platform that is 1 meter above the ground. The 6 o'clock position on the Ferris wheel is level with the loading platform. The wheel completes 1 full revolution in 4 minutes. How many minutes of the ride are spent higher than 38 meters above the ground? Give your answer correct to the nearest second. Okay, so just as a way to picture this problem, we have a Ferris wheel that has a diameter of 45 meters, and it's on this platform that is 1 meter above the ground. Okay, so I know my amplitude is that with this midline, we're going 22.5 up and 22.5 down eventually. So my amplitude, which is the absolute value of A, is 22.5. Now my midline is y equals 23.5 because I have 22.5 here and adding on that 1 meter high platform gives me a midline of 23.5. Now I know that my period is 4 minutes, and we can get good information from this. Remember, your period is 2 pi over b. So if I multiply both sides by b and divide by 4, I know that b is pi over 2. So now I'm ready to put the function together. Let's go ahead and call this h of t, the height at time t. Height at time t is going to be my a. I know my amplitude is 22.5, but I'm going to have a reflection here, negative 22.5, so that I can start at the lowest. Okay, so I want my height to be starting at the lowest at 1, and then go up from there, so that I'm going to be using a cosine function. Okay, so it's going to require a reflection, so I know my a is negative 22.5. Cosine of pi over 2 t, and shifting it up 23.5 so that we can get to that midline. Now we want to know how many minutes of the ride are spent more than 38 meters above the ground. So we have an equation to solve here. I have 38 as my height at some time t is equal to negative 22.5 cosine of pi over 2 t plus 23.5. Now solving, I'm going to go ahead and subtract 23.5 from both sides, and I'll divide by a negative 22.5 after that. That gives me a negative 0.64 is equal to the cosine of pi over 2t. Now I'm ready to use inverse cosine. So the inverse cosine of negative 0.64 is equal to pi over 2t. Now multiplying both sides by 2 and dividing by pi, I'll have t equals 2 inverse cosine of negative 0.64 divided by pi. Now we need to go ahead and get the calculator out. This is not one of our special values. And putting this into the calculator, I have the inverse cosine. Go down to inverse cosine in the trig menu. Inverse cosine of negative 0.64. And there we are at 2.27 radians. So this number here of inverse cosine negative 0.64 I can replace with 2.27. Of course, keep that exact value in your calculator to use so you don't have round off later. Dividing by pi. Now, if you think about here, the cosine function on the unit circle, 2.27 about right here, and that's where the cosine is negative 0.64. But that also occurs down here. Okay, so if we would take 2 pi and subtract that 2.265, we have about 4.01 is the other place where the cosine is negative 0.64. That makes sense because you're going to hit this height at a certain time, and then that's on your way up, but then going down you're going to hit that same height again. So we have, or 2 times 4.02 divided by pi is the other time t. So we'll go ahead and put this into the calculator. I have 2 times 2.27 from up in the calculator and divide by pi, and I get a time of approximately 1.44. That's 1.44 minutes. And the other time is going to be 2 times that 4.01 there and divided by pi, and that time is approximately 2.56. So between the times of 1.44 minutes and 2.56 minutes, you are above the 38 meters above the ground. So let's go ahead and subtract those to find the total time. So we're going to take that and subtract the first time that you hit that height, and that's going to be a time of approximately 1.11 minutes. Now, we do want to get the answer correct to the nearest second, and this is in minutes. So I know that I do have 1 full minute. This is 1 minute. And I'm going to take and subtract that 1 minute from the calculator. So subtracting 1 from that, this is 0.11 minutes. And if I can multiply that by 60 seconds in 1 minute, then I get about 7 seconds. So 1 minute, 7 seconds. You're going to be 38 meters above the ground. Simple harmonic motion. A type of motion described as simple harmonic motion involves a restoring force, but assumes that the motion will continue forever. Imagine a weighted object hanging on a spring. When that object is not disturbed, we say that the object is at rest or in equilibrium. If the object is pulled down and then released, the force of the spring pulls back the object towards equilibrium and harmonic motion begins. The restoring force is directly proportional to the displacement of the object from its equilibrium point. When time equals 0, then d equals 0. Time of 0, displacement of 0. We see that simple harmonic motion equations are given in terms of displacement. Displacement d is equal to a cosine of omega t, or d equals a sine of omega t. Absolute value of a is the amplitude. 2 pi over omega is the period, and omega over 2 pi is the frequency, or the number of cycles per unit of time. Now let's talk about damped harmonic motion. In reality, a pendulum does not swing back and forth forever, nor does an object on a spring bounce up and down forever. Eventually, the pendulum stops swinging and the object stops bouncing, and both return to equilibrium. Periodic motion, in which an energy dissipating force or damping factor acts, is known as damped harmonic motion. Friction is typically the damping factor. In physics, various formulas are used to account for the damping factor on the moving object. Some of these are calculus-based formulas that involve derivatives. For our purposes, we will use formulas for basic damped harmonic motion models. In damped harmonic motion, the displacement of an oscillating object from its rest position at time t is given as f of t equals a times e to the negative ct times the sine of omega t, or f of t equals a e to the negative ct times the cosine of omega t. C is a damping factor. Absolute value of A is the initial displacement, and 2 pi over omega is the period. A spring oscillates with a frequency of 4.5 cycles per second. Its initial displacement is 15 centimeters and its damping factor is 0.2. Give the function f of t that describes the position of the spring t seconds after it starts oscillating. I know that my frequency here, frequency is going to be, remember, omega over 2 pi, and it says the frequency is 4.5. In this way I can solve for omega. Multiplying both sides by 2 pi, I know that omega is 9 pi. And then I know that my initial displacement is the absolute value of A, which is 15, given in the problem. And I have a damping factor of C, which is 0.2. Now I have a couple of options to choose from. I could use the sine function or the cosine function. So let's walk through how to know which one to use. Let's go ahead and write both of these out. The first one, if I'm using the sine function, would be 15e to the negative 0.2 t sine of 9 pi t. Or we could have the cosine function, 15e to the negative 0.2 t cosine of 9 pi t. Now, what happens when time is 0? When time is 0, I have here the sign of 0. And I know that the sign of 0 is 0. And this would be also a 0. E to the 0 is 1. But my f of t would end up equaling 0. So my initial displacement is not correct. I need to have an initial displacement of 15 centimeters. That way I know this is not going to be correct. Let's say that I used the time of 0 for the second function. If time is 0 here and here, we'd be taking the cosine of 0, which is 1. E to the 0 is 1, so now I have 1 times 1 times 15. So at a time of 0, meaning initial time, my displacement, f of t, is 15. So in that way, it's easy to choose which function is the correct function to use.